Hey everyone, welcome back to Everything is Relative with me, Mr. K. And today we're going to be doing more topical past paper questions from Papa Cambridge, this time on the topic of thermal properties of materials, and this is for Cambridge A-level physics. Now, thermal properties of materials puts together the questions from temperature, the topic of temperature, and the topic of thermodynamics. And so some of these questions will come from each of these topics. Today we're only looking at questions 51 to 56, which are mostly around the topic of temperature. And in a later video, I will look at the questions that are focusing more on thermodynamics, on the first law, etc. And so today, again, I will link the questions in the description below. Feel free to download these topical past paper questions and use them in your preparation for your exams, and then use these videos as a guide to help you whenever you get stuck solving any of these problems, or if you need any assistance when answering any of these problems. So the numbering is a little bit hazy. And so the first question is question 51. And as always, the subject code is 9702 for A-level physics. This comes from the March 2021 exam. And this is from question paper 4, variant 2. And this is question number 3 from that paper. And the question says, use a simple kinetic model of matter to describe the structure of a solid. Now, this is A-level physics, but this question may as well be IGCSE, because if you've done O-levels or GCSEs, you would know that this question is a common type of high school question. How can we describe what a solid looks like if we think about a kinetic model of matter, talking about the particles themselves? So what we know about solids is that in solids, particles are very close together. And we have to think about what the particles do when they're very close together. Well, they are firstly in a regular arrangement. So if I look at a solid, then I should see many particles arranged in very similar ways. They don't need to be arranged like a crystal does, but they still will have a regular arrangement. And it's wrong to think that they don't move at all. They do move, but they aren't free to move as they would be in a liquid or in a gas. So how do they move? They simply vibrate about fixed points. So molecules or particles or atoms or whatever you want to say vibrate about fixed points. And that will describe what a solid looks like if we think about their specific particles or molecules or atoms. You could use either word when you're talking about the description. Part B says the specific latent heat of vaporization is much greater than the specific latent heat of fusion for the same substance. Explain this in terms of the spacing of molecules. So this question is a lot more tricky. Why is it that for every substance, the latent heat of vaporization is always greater than the latent heat of fusion? Remember what the latent heat of vaporization is. It is the amount of energy per unit mass that is required to change the state from a liquid to a gas. Let's look at liquid to gas in this case. From a liquid to a gas, and the specific latent heat, and without changing in temperature, of course. And the specific latent heat of fusion is changing the substance from a solid to a liquid, again without change in temperature. But remember, changing from a solid to liquid, all we do is sort of loosen or weaken the bonds. We don't fully break the bonds. Whereas with vaporization, from a liquid to a gas, we allow the gas molecules to be completely free, to have no attachment, no potential energy linking them to any other molecules. So in terms of spacing, we have to be very careful how we state this. So what we know is that, yes, gases have greater spacing than liquids, but that doesn't answer our question. What happens is that the increase or the difference in spacing, we can say increase or difference in spacing between molecules after vaporization, after they have been vaporized, they've been turned to steam, water turning to steam, for example, is much larger, is much greater than that of fusion. And you can go on to speak about the reasons that I've spoke, because the increase in spacing is because when we go from a solid to a gas, we are completely breaking the bonds, whereas when we go from a liquid, or rather from a solid to a liquid, we are simply weakening the bonds. The bonds still exist, they are just weaker. And so even though liquids can flow, they are still constrained and still confined to flow with the surrounding molecules. And so the increase, the difference in spacing between molecules after vaporization is greater than the difference in spacing than after fusion has happened, or after melting has happened. And so that's the way you would answer this question. It's a common type of question, but you must talk about the difference in spacing, not just particularly the spacing. Because remember, latent heats talk about the situation between states, what's happening between states. So we have to talk about the state before and the state after, not specifically about one state. Question C says a heater supplies energy at a constant rate to 0.045 kilograms of a substance. The variation with time of the temperature of the substance is shown in the figure below, and the substance is perfectly insulated from its surroundings. So I have some substance, maybe it's water, maybe it's something else, but you can see its temperature increases, and then while supplying heat, there's suddenly no temperature increase, and then again temperature increases, and then while still supplying the same amount of heat, there's a long time where no temperature increase happens, and then again the temperature increase happens. So you can see that this graph has some oddities to it. But again, if you study this subject in detail, or this topic in detail, you'll know why this happens. Now, the first thing they ask us to do is to determine the temperature at which the substance melts. So what I have here is there's 3 states of the substance, and when the substance is properly in those states, it is increasing in temperature. And between those states, the temperature doesn't change because thermal energy is being used to break the bonds between molecules. And so my 3 states are represented by my 3 diagonal lines, the 3 lines that have some gradient. And so I have the solid state, then P would be the liquid state, and then Q would be my gaseous state. And so if I want the temperature at which the substance melts, I want the temperature when it's going from solid to liquid, and that's where the thermal energy is constant because the solid bonds are being weakened to form a liquid. And that we can see from reading off of the graph. You don't have to go through all of this logic, but in your mind you can immediately see that that's minus 100 degrees Celsius. And the unit's already degrees Celsius, so I just need to write the number minus 100. Now we are then told that the power of the heater is 150 watts, and we want to use data in the figure to calculate in kilojoules per kg the specific latent heat of vaporization L of the substance. Well, how do I do this? I know the power, and I want to find the latent heat of vaporization. Now I know the latent heat of vaporization occurs between, 3 minutes and 8.5 minutes. So this flat horizontal line on top, where all of the liquid bonds are being broken to form the free gas molecules, and in that time no thermal energy goes to increase the temperature of the liquid, but rather to break those bonds. So that's from 3 minutes to 8.5 minutes. So I know that's the time in which vaporization is happening. Now, what do I remember? I remember that energy Q is equal to, thermal energy rather, is the mass of the liquid that's being vaporized times the latent heat of vaporization. But I don't have the energy. I do, however, have the power and the time. So the power multiplied by the time is the thermal energy, since power is energy divided by time. Which means I can rearrange this to solve for the latent heat of vaporization. L is P times T over M. And this is a power of 150 watts times a time of 8.5 minutes. Again, you could do this in your head, but I always suggest not to, in case you make an error, a simple mathematical error that you shouldn't make. So 8.5 minutes minus 3 minutes, and guess what? We're going to multiply that by 60. Again, you could do this in your head, but rather be safe than sorry. Divided by the mass of the liquid, which we were told is 0.045 kilograms. And we calculate this to be 1.1 times 10 to the power 6 joules per kg. But be very careful what answer you write in the next line. The answer wants it in kilojoules per kg. So I'm going to write down 1.1 times 10 to the power 3 kilojoules per kg, because this is 1.1 million joules per kg, which is 1.1 times 10 to the power 3 kilojoules per kg, 1100 kilojoules per kg. Next, they want us to suggest what can be deduced from the fact that section Q on the graph is less steep than section P. So Q is when the substance is in gaseous form, and P is when the substance is in liquid form. So what we can see is the gradient for P is much steeper than the gradient for Q. So what this means is that the temperature of the liquid increases much more rapidly if I'm supplying heat at a constant rate. But the gas takes longer to heat. That means it requires less energy to heat the liquid than it does to heat the gas. The gas requires more energy to heat, so its temperature increases more slowly. Now, I know a specific term or a phrase for things that require energy to change the temperature. We call that thing the specific heat capacity. So what I can judge from this is that since gas is represented by section Q and it is less steep, the gas has a higher, and very importantly, the phrase is specific heat capacity, because specific heat capacity is the amount of energy required to raise the temperature of a unit mass of substance. So the gas has a specific heat capacity that's higher than that of the liquid for the same substance. And so that information from the graph can give you, or just the graph alone can give you quite a lot of information. We can take a lot of information from the graph and we can immediately see that the value for the specific heat capacity will be higher for the gas than it will be for the liquid in the same substance. That is a very interesting question. The questions generally in this topic tend to be quite interesting. Well, interesting for the person setting the exam, I guess, not so much for you. The next question is number 52. This is from the March 2020 exam. This is question paper 4, variant 2, and this is question 2 from that paper. And we are told that a large container of volume 85 cubic meters is filled with 110 kgs of an ideal gas. The pressure of the gas is 1 times 10 to the 5 pascals, and the mass of 1 mole of the gas is 32 grams. Show that the temperature is approximately 300 Kelvin. So we know immediately, if somebody's giving us this much information, they want us to use the ideal gas equation. However, they give us the mass of the gas rather than giving us the number of moles, the number of molecules. At least we do have the molar mass. They told us the mass of a mole is 32 grams. So what we can do is first say, well, the number of moles is the number of substance I have, the mass of the substance I have, divided by the mass of the mole, molar mass. And the ideal gas equation is PV equal to nRT, which means that if I want to find the temperature, temperature is PV divided by nR, which, if I replace little n, is big M times pressure times volume divided by mass little m times R, where R here is the universal gas constant. And so now I actually have enough information to find this temperature. So this mass is 32 kilograms, 32 times 10 to the minus 3 kilograms, 32 grams rather, which is 32 times 10 to the minus 3 kg, multiplied by the pressure, which is already in OK units, in SI units, so that's 1 times 10 to the power 5 pascals, multiplied by the volume, also in OK units, 85 cubic meters, divided by the mass of the substance I have, which is 110 kilograms, times the gas constant 8.31. And guess what? If I put this into a calculator, what I get is 297.6 Kelvin. But the question did say, show that the temperature is approximately 300. And that's good enough for me. That's approximately 300 Kelvin, as we were asked. So the only trick there was, once I have the ideal gas equation written down and rearranged it, since I don't have the number of moles, I can use the mass and the molar mass to find the number of moles of the gas. A little bit of chemistry there. Part B says the temperature of the gas is increased to 350 Kelvin at constant volume, and the specific heat capacity of the gas for this change is 0.66 joule per kg per Kelvin. Calculate the energy supplied to the gas by heating. Now, the energy supplied to any substance by heating is thermal energy, and for a change in temperature, specifically change in temperature without change in state, Q is mc delta T. Well, I know the mass of the substance, it's 110 kgs. I'm given the specific heat capacity in the correct units, joule per kg per Kelvin, 0.66. And the temperature change goes from 300 to 350 Kelvin, so that change in temperature is 50. And maybe I should just write it down for clarity's sake. It's 350 minus 300. Remember, when calculating temperature difference, you can use Kelvin or degrees Celsius, because the difference in those two temperatures are the same numerically. And so Q will be 3.63 times 10 to the power 3 joules. So to two significant figures, this thermal energy to heat the gas by 50 Kelvin is 3,600 joules, or 3.6 times 10 to the power 3 joules. Now, part C says explain how movement of the gas molecules causes pressure in the container. This is a very common question. You know how to do it, and you're going to be asked to do it. Probably very likely that you would see a question similar to this. So how does pressure happen in the container? So firstly, we know that gas molecules collide with each other, but more importantly, they collide with the walls of the containing vessel, or the walls of the container. That doesn't tell us immediately that there's pressure, but what it does tell us is that the momentum changes in the process. So the gas molecules collide with the walls of the container, but if they strike the wall and come back in the direction that they were initially traveling, or opposite to the direction in which they were originally traveling, then the momentum changes. Momentum's a vector, so the momentum will change. But we also know that the change in momentum means that there's a force on the molecules. So the force on the molecules, which happens when their momentum changes, means that there is a force on the wall with which it collided. So if the molecules feel forces, then the walls also feel forces with these collisions. That's all collisions do, because of Newton's third law. Newton's third law says if you're going to impart a force on the wall, the wall's going to impart a force on you, and vice versa. And what we have is more than one collision. So we have many forces acting over the entire surface area of the wall. So acting over the wall's surface area. And what do we know? That force over a given area, force per unit area, results in pressure. So that's using the kinetic theory to explain how pressure occurs in gases. Again, like I say, it's a common type of an exam problem. You need to understand how the kinetic theory relates to pressure. What is pressure when we think about things on the molecular scale? It's all well and good to measure pressure and to say this on a macroscopic scale, here's the pressure of the gas, but what is it actually telling us? It's basically telling us this. Molecules collide with the walls of the container and they change momentum. That means there's a force on them. That means there's a force on the walls as well. Many of these forces over the wall's entire surface area results in a pressure, since pressure is force per unit area. And so you have a lot of lines. You can make better use and more use of the lines than I have, but I think I've explained everything that you want to see in that answer. Make it as clear and concise and remove any contradictions that you may have when writing these answers. But that was a very conceptual kind of question. Next, we are told that the temperature of a gas depends on the root mean square, the RMS speed of the molecules, and we are asked to calculate the ratio of the RMS speed of gas molecules at 350 Kelvin to the RMS speed of gas molecules at 300 Kelvin. Now, I know that RMS speeds are not all of your best friends, But how do I do that if I'm only told that the temperature depends on the root mean square of the molecules? Well, actually, this helps quite a lot. They tell me that the temperature depends on the root mean square of the molecules. Doesn't tell me the whole story, but tells me that there's some relationship. Now, to think about this relationship, I know that the kinetic energy of the molecules, of the entire gas rather, is a half mc squared. But we have to take the average of the c squareds of all the molecules. So we take the mean square speed. So I got c squared inside the brackets for average, the mean square speed. And what I also know is that Ek is equal to 3 over 2 K times T, or it's proportional to temperature. So what this means, and you don't need to write the first bit that I've done, but what this means is you need to remember that mean square speed is proportional to temperature. Not root mean square, but mean square speed. Which then means that the RMS speed of molecules, which by definition is the square root of the mean square, if I block off the word root, I get mean square. If I square root the whole thing, I get root mean square. So it's the square root of the mean square speed, which is the RMS, which is obviously then proportional to a square root in temperature. So I have to square root the temperature, which then means that my RMS speed, CRMS, so I don't really need to know the definition of RMS, but I need to know how it relates to mean square. So the RMS speed at 350 Kelvin divided by the RMS speeds at 300 Kelvin is the square root of the difference in temperatures. Square root of the two temperatures. 350 divided by 300. So it simplifies quite easily. And what I get is a ratio of 1.08. Always keep your ratios as decimal numbers. And that's because we can preserve the number of significant figures. In this case, I'm going to use 2, and I get a ratio of 1.1. So the speeds of the molecules at 350 Kelvin is 1.1 times the speed of the molecules at 300 Kelvin, which kind of makes sense. You'd expect the molecules to be moving around faster on average as the temperature of the gas goes up. So always remember, if you don't remember how c squared is related to t, or the actual equation rather, just remember that c squared is proportional to t, and everything else will fall in place. Okay? You don't need to remember the actual equation that c squared is related to t with, but at least the proportionality. So that was a fairly long question, altogether 10 marks, and a significant portion. I mean, your paper 4 exam is 100 marks, a 10-mark question is 10% of that exam. So important to understand your thermal properties. The next question is question 53, and this comes from the winter 2019 exam. This is question paper 4, variant 1, and this is question 3 from that paper. And the first thing they say is, where we're waiting for a question like this, state what is meant by specific latent heat. So this again is something that you can do in your sleep. It is the thermal energy. Don't forget the per unit mass because of the word specific. It's a thermal energy per unit mass that's required to change the state of a substance. We're not done there. This is not the definition. We have to include that the temperature must remain constant. So at constant temperature. So it's the amount of energy that I need to take a unit mass, 1 kilogram of mass, and change its state from solid to liquid, from liquid to gas, from gas to liquid, liquid to solid, without changing its temperature. So it specifically is an amount of thermal energy. Next, we are told that a student determines the specific latent heat of vaporization of a liquid using the apparatus illustrated. You can see we have an ammeter, we have an electric heater inside the liquid, and then a voltmeter to calculate the potential difference, and a pan of balance, or a balance pan. The heater is switched on, and when the liquid is boiling at a constant rate, the balance reading is noted at 2-minute intervals. After 10 minutes, the current in the heater is reduced, and the balance readings are taken for a further 12 minutes. So obviously we're going to get a graph here. And we are told that for the first 10 minutes, this is the ammeter and voltmeter readings. After 10 minutes, we change the ammeter and voltmeter reading. And so what we get is the balance reading in grams against time in minutes. Now the balance reading is going to decrease as we heat the water and some of it boils away. So what is it actually telling us? The change in mass that's shown on the balance is equal to the amount of water, I'm saying water rather, the amount of liquid that's evaporating, the amount of liquid that is undergoing vaporization. That's all it's telling us. The balance being there is just an extra piece of the puzzle. That's how a way we can actually calculate the amount of liquid that's being evaporated. So we are told that from time 0 to 10 minutes, the mass of liquid evaporated is 56 grams. And we are then told to use figure 3.3 to determine the mass of liquid evaporated from time 12 minutes to time 22 minutes. So the first 10 minutes thankfully is given. We could have got it from the graph, but it's much better if they do give it to us. And they want us to find the mass of liquid evaporated from 12 to 22. Not from 10 to 22, but specifically 12 to 22 minutes. How much of liquid has evaporated? Well, what I need to do is I need to see what mass I had at 12 minutes and what mass I had at 22 minutes. And if I subtract the two, then I know how much of the mass has been lost because it's been evaporated. So I could do this again. I could do this in my head. I prefer not to. I'd rather write it down in pencil. I had 424 grams. After 22 minutes, I have 392 grams. So 424 grams at the time of 12 minutes. And the difference is 32 grams. I will even use my calculator to do that to make sure I don't make a mistake. So the mass of liquid evaporated is 32 grams. Now you can see they gave us two masses, so in the back of your mind, you probably know you're going to need them later on. We're then told to explain why, although the power of the heater has changed, the rate of loss of thermal energy to the surroundings may be assumed to be constant. So if I'm changing the power of the heater, I'm changing how much of energy I'm giving to the heater, or to the liquid rather, every second. So you'd expect, well, not expect, but in your mind, they're trying to get you to think that, well, the rate at which the energy is being passed to the surroundings will also change because now I'm heating the water more rapidly. But I want you to think back to what we said when learning about thermal physics, when learning about temperature. We remember that the temperature difference is the thing that determines the rate of heat transfer, the rate at which energy is passed on to surrounding objects. But the temperature difference doesn't change. The temperature difference between the liquid, whatever liquid it may be, and the surroundings remains the same. And if the temperature difference between the liquid and the surroundings remains the same, since the liquid is constantly boiling, even if we change the power of the heater, it's still at 100 degrees, well, actually I'm using 100 degrees, but whatever the boiling point of the liquid is, it's a constant value. So the temperature difference between the liquid and the surroundings remain the same. So the rate it loses energy to the surroundings won't change. So as long as two cups of coffee are placed together and they have the same temperature difference, then they will always pass thermal energy. One will pass thermal energy to the other at the same rate because the temperature difference remains the same. So that piece of information also seems like I might need it again. It turns out that I do. It turns out that these first two pieces of information are important for the third part of the question, which is a tricky question. Determine a value for the specific latent heat of vaporization of the liquid. Okay, so this kind of question, and it's very possible that it could be a question that will stump you. And in all fairness, it's not an easy question. So just remember, whenever I want to find latent heat of vaporization, I'm going to turn to my energy equations, my equations for thermal energy. I have one equation that contains a specific latent heat and another equation that contains a specific heat capacity. I'm only looking for the latent heat of vaporization, so I don't need the heat capacity equation here. So what I can tell is the first amount of energy required, Q1, which I don't have, is equal to power times time, electrical power times time. But wait a minute, electrical power is V times I. It is the potential difference measured across the heater times the current through the heater. That gives us the power through the heater. And then we multiply that by the time, and we get the total amount of energy given to the heater, which is the total amount of energy given to the liquid. And the total amount of energy given to the liquid, some of it goes into vaporizing the liquid, some of it is lost. Very careful. We call this term, you can name it whatever you like, K, H, whatever. I use H for heat loss. But some of this energy is lost to the surroundings. So some goes to actually vaporizing the liquid, but some of it is lost to the surroundings. This is why we always close our kettles, and rather than leaving our kettle, the top of the kettle or the lid of the kettle open when heating water. So we reduce the amount of heat loss. Now, when the power is changed, when the gradient of this graph shifts, and we have a second value, after 10 minutes that is, or even after 12 minutes as the data that we were given suggests, then there's a new total amount of energy going to the liquid. It's V2, I2, T2. I just labeled 1 and 2 as the two different happenings, the two different occurrences here. The first voltage and current and the second voltage and current. This is equal to the new mass of liquid that has evaporated times the latent heat of vaporization, which remains constant, plus some other amount of energy which is lost to the environment. And this will be a different value. The actual amount of energy lost to the environment is different. So this equation as it is not going to help me very much. However, what I can do is I can try something very clever. I can take these two equations and I can divide them both by T. If I divide through by T, what I get is V1 I1 is equal to M1L over T over T1 plus H1 over T1. And then my second equation becomes V2. Look, there are many ways of solving this problem. I like doing the mathematical route, but it's completely up to you. M2L over T2 plus H2 over T2. Now, why did I do this? Because these two terms, the last term on each of these equations, H1 over T1, must equal H2 over T2. Why? Why do I say that? Because the rate at which energy is lost will remain the same. So the total amount of energy divided by the time over which that energy is lost to the surroundings must be the same. Aha, so I can now take one of these equations and subtract the other. So if I call the second equation number 2 and the first equation number 1, I can say 1 minus 2 and I can get rid of those terms on the end. So I have two equations and I can solve them simultaneously. So what I get is I'm going to take the first equation and subtract the second equation. V1 I1 minus V2 I2 is equal to L into M1 over T1 minus M2 over T2. Wow. Which then means I can rearrange and solve for L. And it looks messy, but it actually is a lot cleaner doing it this way than having to put in values and trying to play around with values and so on. It's a lot easier to do it algebraically and then do the arithmetic. So I rearrange this equation and I can find everything else. The voltages are given, the currents are given, the masses are given, and so too are the times. And so now I know I have done all the work in the previous questions. And what I can also do is I can leave my masses in grams because they want L to be calculated in joules per gram. Okay, so what do I get? I get V1 I1, which is 230 volts and 1.2 amperes, so 230 volts times 1.2 minus V2 I2, which is 190 volts times 1 ampere divided by M1 over T1 is a loss of 56 grams. 56 grams of liquid has boiled away in a time of 10 minutes. So I have to convert that to seconds, so that's divided by 600 minus, in the next 10 minutes I lost 32 grams, from 12 to 22 minutes. So that's 32 grams also in 600 seconds. And if you do the calculation, you get L to be 2.15 times 10 to the power 3 joules per gram. Or to two significant figures, 2.2 times 10 to the power 3 joules per gram. Now, this was a tough question, but all you needed to do is remember that there must be a term for heat loss, because otherwise you'd have too many things to otherwise you'd get an answer that wouldn't be correct. But when you have the heat loss equation, we can always change that to a power equation, and the rate of heat loss disappears, which then makes the calculation a lot easier. And so the rest of it is just mathematics and simple rearranging. But this is a kind of question that I've seen a few times in past exams, so make sure you understand what I've done here. But we had to account for heat loss, and the previous questions actually give us a hint. So there's a very strong hint. So always look for these previous sub-questions, think of them as hints to the question that you're trying to solve, especially if they're labeled with Roman numeral 1, 2, and 3. You can use those hints to make some inroads into solving the kind of problem. Roman numeral 4 says calculate the rate at which thermal energy is transferred to the surroundings. Well, thanks for letting us know, but we've already done the hard work. They want me to find H1 over T1 or H2 over T2. Those two are going to be the same. So I'm going to use the equation that has H1 over T1 in it, which is V1I1 minus M1L divided by T1. And then I can go back and use my equation for my value for L that I've calculated and solve for this. So this is 1.2 times the voltage 230 volts minus 56. I can leave my mass in grams because L is also in joules per gram. So 56 times 2.15 times 10 to the power 3 joules per gram. And that's in a time of 600 seconds. And so what I get is the rate being 75.3 watts. Or to two significant figures, 75 watts. So calculating the rate at which thermal energy is transferred to the surroundings is fairly easy because I had it already done in my equations above. Again, you could even use this subsequent question as a little bit of a hint as to the way you would go about setting up your answer for the previous question. So if we look close enough, there are enough hints to help us solve difficult problems. And that, I think, was one of them. I think fair enough, that question was a relatively tough one. The next question is number 54. And this comes from the exam of winter 2019. So winter being November, December. And this is question paper 4, variant 2, and question number 3 from that paper. The first thing they ask us is to state what is meant by specific latent heat. Well, guess what? We've done it already. Specific latent heat is the thermal energy per unit mass to change the temperature or to change the state of a substance without changing its temperature or at a constant temperature. So the thermal energy per unit mass to change only the state of a substance without changing its temperature or changing the state at a constant temperature. And this question actually looks a lot similar to the previous one, but we have ice rather than liquid here. So a student uses the apparatus to determine a value for the specific latent heat of fusion for ice. The balance reading, like before, measures the mass of the beaker, so it measures the amount of ice that is melted. The heater is switched on, and pieces of ice at 0 degrees Celsius are added continuously to the funnel so that the heater is always surrounded by ice. So when water drips out of the funnel at a constant rate, the balance reading is noted at 2-minute intervals. With a lot of similarities to the previous question. After 10 minutes, the current in the heater is increased and the balance readings are taken for a further 12 minutes. Actually, eerily similar to the previous question. We're given the variation with time of the balance reading as shown in the figure, and again we have two sections. We have 10 minutes and then a further 12 minutes, and we can see the graph changing. And that's because the ammeter and voltmeter readings, which is the power by the current and the potential difference given to the heater, changes. And well, the questions also share similarity. From 0 to 10 minutes, 65 grams of ice is melted. They want us to use the figure to determine the mass of ice melted from 12 to 22 minutes. So specifically the next 10 minutes, from 12 to 22 minutes. How much of ice has melted? Well, I need to see how much of ice I had at 12 minutes and how much of ice I had at, or rather how much of water I have at 12 minutes and how much of water I have at 22 minutes, and subtract the two. And that's how I know how much of ice is melted. So I measure the mass of the water at 22 minutes to be 285 grams, and the mass of water I had at 12 minutes was less, it was 145 grams. So again, I do this calculation to prevent me from making any mistakes, and I get a difference of 140 grams. So the mass would be 140 grams. That's the amount of ice that is melted in that time. We're then told to explain why, although the power of the heater has changed, the rate at which thermal energy is transferred from the surroundings to the ice is constant. So the one difference that we have here to the previous question is that in the previous question, the heat from the heater was going to boil the water, and then some of that heat was being lost to the surroundings. In this case, the surroundings are warmer than the ice. So we assume the surroundings are at room temperature. So the surroundings are warmer than the ice, so some of the energy of the heater goes to heating the ice, and some of the energy of the surroundings helps the heater melt the ice. So why do we want to say that? So this is why we say energy is transferred from the surroundings to the ice, and the rate at which it happens, the word rate is important, is constant. The reasoning is exactly the same. There's no difference between the reasoning in this question and the reasoning in the previous question. The temperature difference. If you haven't done the previous question, I would strongly suggest you do that question because it's very similar to this one. The temperature difference between the ice and the surroundings doesn't change. So the ice would still be at 0 degrees and the surroundings would still be at whatever temperature the surroundings are at. Since the temperature difference is constant, the rate at which thermal energy flows into the ice from the surroundings will remain constant. Not the total energy. The total energy will depend on the time, but the rate at which it flows will be the same because the temperature difference is the same. And again, they ask us to determine a value for the specific latent heat, but this time it's a specific latent heat of fusion for ice. So I'm going to do exactly the same thing I did the last time. In the first 10 minutes, I'm going to call the energy going to the ice Q1, and this is equal to the power times the time. The power for an electric heater is the voltage across the heater V1 times the current in the heater I1 times the time over which the energy is supplied T1, power times time. And from thermal physics, this is equal to the mass of ice melted times the latent heat of fusion for ice minus the heat loss or the heat gain from the surroundings. So basically in this case, it is Q1 plus H giving me ML. So it's heater power plus external help gives me the mass of water melted, mass of ice melted times the latent heat of fusion. And so I have a minus sign. Mathematically, that's really all what that's going to change, and everything else will be the same. For the second 10 minutes, V2, I2, T2 is equal to the new mass of ice that is melted, M2 times the same constant L, minus a different amount of energy because the time is different. And I'm going to do the exact same thing I did before. I'm going to divide through by T on both sides of this equation. So I get V1, I1 is equal to M1L over T1 minus H1 over T1. And the second equation becomes V2, I2 is equal to M2L over T2 minus H2 over T2. And what can I tell? Well, I can tell the exact same thing again. The rate at which the heat is taken from the surroundings will be the same because the temperature difference is the same. So H1 over T1 is H2 over T2. So I can do some mathematic and I can subtract one equation from the other. Whichever way you subtract is completely up to you. I'll subtract the second equation from the first. So I'm going to get V1 I1 minus V2 I2 equal to the latent heat of fusion L into M1 over T1 minus M2 over T2. Guess what? The only unknown is L. So I can rearrange this equation and solve for L. And so if I put the values in, I get L is equal to V1 I1, which is 7.3 volts times 1.8 amperes minus 15.1 volts times 3.6 amperes. We need a lot less energy from the heater than we did before because melting is a lot easier than boiling. And this is divided by both of these masses. We're going to use the masses that we calculated, which were both for periods of 10 minutes. So that's 65 minus 140 divided by 10 minutes, which is 600 seconds. And we get the latent heat of fusion for ice to be 326.88 joules per gram. Again, we left our mass in grams because the answer asked us for joules per gram. And then so I can write that in two significant figures as 330 joules per gram, which if you know your values from your tables of specific latent heats, you'll know that the latent heat of fusion for ice is roughly this value, 330 joules per gram. And so we use exactly the same method, but the only mathematical change was since we were gaining energy from the surroundings, what we had was a minus sign for the heat loss on either side, minus H1 and minus H2. And that's all that really happened. Everything else was exactly the same, it was analogous to the previous question. And you could even guess what the next question was going to be. Calculate the rate at which thermal energy is transferred from the surroundings to the ice. And so I can say H1 over T1 or H2 over T2, whichever is comfortable for you, and rearrange the equation that has that in it. Is M1L over T1 minus V1 I1, which is 65 grams times 330 joules per gram. So my numerator is in joules, divided by a time of 10 minutes, which is 600 seconds, minus the voltage and current for that specific time period was 7.3 times 1.8. And so what I get is 22.61 watts, again to two significant figures, 23 watts of power. And so that's the rate at which thermal energy is being transferred from the surrounding air to the ice. In the previous question, the heat was going from the boiling water to the surrounding air because the boiling water was at a higher temperature than the surrounding air. And so you have to think about the scenario. You have to think about whether I'm boiling or melting. And you're going to have to think about, well, are the surroundings at a higher temperature or a lower temperature? And then everything else is basic mathematics, which might require some practice but will not trouble you excessively. Now, the last question we're going to do in this video is question number 56. Again, subject code 9702. This is from the summer exam, May-June 2018. This is question paper 4, variant 2, and question 3 from that paper. We're told that during melting, a solid becomes liquid with little or no change in volume. And we want to use kinetic theory to explain why, during the melting process, thermal energy is required, although there's no change in temperature. So temperature doesn't change during melting, as it doesn't change during boiling as well. but we want to know why thermal energy is still required. So we mentioned this before, but we now need to mention it formally as well. Thermal energy is required not to change the temperature, but required to break the bonds. And this is specifically to break the bonds between molecules. And what does this do when the bonds are broken between molecules? We don't really change their kinetic energy much, but we increase their potential energy. So thermal energy is required firstly to break the bonds between molecules and increase the potential energy of those molecules. We don't really move the molecules in this process, so we can say that little or no work is done, and so thermal energy is required. Since we aren't doing mechanical work on the particles, or doing very little mechanical work on the particles, the energy that we require must be in the form of thermal energy, and this energy is required to firstly break the bonds and increase the potential energy of the molecules that feel the bonds. And so this is how you would explain, using kinetic theory, why in the melting process or even in the boiling process thermal energy is required and there isn't any change in temperature. Remember, little or no work is done, there's no change in kinetic energy, but most of the energy change is potential. Next, we are told that an aluminium can has a mass of 160 grams and contains a mass of 330 grams of warm water at a temperature of 38 degrees Celsius. A mass of 48 grams of ice at minus 18 degrees Celsius is taken from a freezer and put into the water. The ice melts and the final temperature of the can and its contents is 23 degrees Celsius. We are given the specific heat capacities for aluminium, ice, and water in joules per gram per Kelvin. And we are told that assuming no exchange of thermal energy with the surroundings, we are asked to calculate, or rather show, that the loss in thermal energy of the can and the warm water is 2.3 times 10 to the power 4 joules. Okay, so how do we go about that? At least we're given an answer. We're most likely going to need that answer for the next part of the question. Can we show that that's the loss of thermal energy in the can and the warm water? Now, it's always good in these questions, even though this is kind of written for you, to write your equations in word form. Heat loss by something is equal to heat gain in something. I think in this way it helps you identify all the things that are gaining energy and all the things that are losing energy. And then going back to your information and filling in those energies specifically. So the heat loss by the can and the water is equal to, now, or the thermal energy loss by the can and the warm water. Now the can is not changing state and the warm water is not changing state either. The water is not freezing and the can is not boiling. So only a change in temperature is happening. So I need my specific heat capacity equation. So the mass of aluminium times the specific heat capacity of aluminium times the temperature change. We use delta theta for temperature change, or delta T, whichever you're comfortable with. And I'll use subscript aluminium plus the same for the water. The warm water, the water that was originally in the can, plus mc delta theta, and I should say warm water. I'm just going to write H2O because, well, I'm lazy. And if I put my values in, this is a mass of 160 grams. I can leave my mass in grams because my specific heat capacity is also given in grams, times the specific heat capacity of aluminium, 0.910, times the temperature change. Again, I'm not going to do this in my head lest I make a mistake. 38 minus 23. Yes, I know this is 15, but again, I'm not going to take that chance of doing a calculation and getting it wrong. And then I have to add this to however much energy the warm water has lost, which is the mass of water, 330 grams, times its specific heat capacity, 4.18 joules per gram per Kelvin, times its temperature change of 38 minus 23. So if the warm water has a final temperature of 23 degrees Celsius, then so too does the aluminium can. So the warm water and the can will have the same final temperature. Remember, they will reach thermal equilibrium. So I'm just going to assume that the can and the warm water have the same final temperature. And what you can always do is use a change in temperature as bigger minus smaller. We don't have to consider negative values. If we're always going to write an energy equation as heat lost by something is equal to heat gained in something, we can just always use our change in temperature as bigger number minus smaller number. So we'll get a positive number on the left-hand side and a positive number on the right-hand side, and they're the same energies. And we can figure out which is going in and which is coming out. Okay, so again, the negative sign will just be for convenience. And if I do this, guess what? I get the heat lost by the can and the water to be 2.3 times 10 to the power 4 joules as required. Now, I know these types of questions are quite sticky. A lot of people don't really enjoy these kinds of questions, but I guarantee with practice, you start to find that if you make it a habit to make a procedure of answering these questions, then the procedure will help you when the question is new and unfamiliar, which it's going to be in your final exam. Write the word equation out, then put it in mathematical form, and then I guarantee you'll find where you're going wrong or right. We're next told to use the information in 1 to calculate a value L for the specific latent heat of fusion of ice. Okay, so what we need to say is, if I think about the energy that I calculated in the beginning, the heat that is lost by the aluminium can and by the water, we'll assume the aluminium can and the water had the same initial temperature and the same final temperature since they are in thermal equilibrium, is equal to the energy that is gained by the ice. Now, we actually can write this slightly better. The heat lost by the can and the water is the heat gain or the thermal energy gained to melt the ice plus the thermal energy gained by the amount of melted ice that has warmed to the final temperature. So I could write this equation even better. I'm not going to write it this way for now because of space, but I know the left-hand side is 2.3 times 10 to the power 4. So the entire right-hand side must be 2.3 times 10 to the power 4. But what's it made of? It's made of the mass of ice times the specific heat capacity of ice times the change in temperature of ice for the ice that has gone from minus 18 degrees Celsius to 0 degrees Celsius. So minus 18 degrees Celsius to 0 degrees Celsius. Plus the mass of ice simply times the latent heat of fusion, which I want to calculate. I'm just going to call it L because they told us to call it L. That is the energy required to melt all of the ice to turn it into water. And now I have some cold water rather than warm water. The mass of the cold water is the initial mass of ice that I had because it's all become water. So I'm going to say the mass of the ice, Mi, times the specific heat capacity, not for ice, but for water, times its temperature change. Maybe I should say, maybe I should just write this as mc delta theta and write a subscript here saying cold water. Or I can say this is the heat gained by melted ice. You can see that if I wrote my first line better, if I included all these words here that I'm writing, if I wrote that in the first line, then it becomes easier to write the mathematical equation. So write as many words as you can in order to make sure that your next step in the calculation is 100% correct. That's a skill that with practice you'll get better at, and then you'll almost always guarantee that what you're calculating will be correct. So then all that's left is very simple algebra. L is, I'm just going to put the values in now, 2.3 times 10 to the power 4 divided by 48. I can leave my masses in grams because I'm asked to calculate L in joules per gram. And this is minus 210 times the temperature change of 18 minus 0. Again, we can always use temperature change as bigger minus smaller. That's for the ice going from ice to 0, where it will actually start to melt, minus the heat capacity for water, 4.18, times the temperature change for the water, the cold water, to go from 0 to 23, so 23 minus 0. And what I get is a latent heat of fusion for the ice to be 345 joules per gram. Or to two significant figures, 350 joules per gram. Remembering our answer from the previous question, that's still roundabout correct what the value for the latent heat of fusion for ice should be. And so if you knew what that value should be, you'd have an idea of the correctness of your answer. But you can see the difficult part was not the mathematics at all. The difficult part was writing a word equation that could then be converted to a mathematical one that will have all the information in it. And so always write a statement that says heat lost by whatever and whatever is equal to heat gained by changing the temperature of ice plus the heat gained for melting the ice plus the heat gained by the cold water which comes from the melted ice to increase its temperature to the final temperature. So there's a lot of words in that word equation, which is why I refrained from writing it down, but eventually that means I would not get the rest of the question wrong. So yes, it's a lot of work for 2 marks, but with practice, that amount of work takes less time. And so you eventually get better at these kinds of problems and they trouble you a lot less. And so this question is, it's worth 7 marks, but it could be take a lot of time. It could be worth a lot of time on your side. And you see all of these questions are on the topic of temperature. And the next video, I will be answering questions that are all or more or less on the topic of thermodynamics. So explaining the work done by expanding or compressing a gas, by the first law of thermodynamics, things like internal energies and so on. I hope this video was useful. Leave a like, a comment, subscribe to the channel if you haven't subscribed already. I'll be posting more of these videos regularly as we get closer to exams. And I'll try to complete all the topics if I can and then move on maybe to paper 5. But let me know if you have any comments or suggestions about this video. For now, that's all from me, Mr. K. I'll see you again next time on Everything is Relative.